Subscribe to Dr. Khalkar's classroom channel and press the bell icon to get latest updates. Hello everyone, I hope you are doing great. In my previous lecture video, I have discussed about free electron theory and Crony-Penny model. In this lecture video, I will discuss about band theory of solids. So let's get started. The content of this lecture video is band theory of solids. First of all, let's get introduced about semiconducting materials. Semiconductor materials come from different groups in the periodic table. It shares certain similarities. The properties of superconductor material are related to their atomic characteristics and change from group to group. Researchers and designers take disadvantage of these differences to improve the design and choose the optimal material for a photovoltaic applications or other applications of semiconducting materials. The atoms in semiconductor are materials from either group 4 of the periodic table or from a combination of group 3 and group 5, which are called as group 3-5 semiconductors, or of combinations from the group 2 and group 6, which are called group 2-6 semiconductors. Because different semiconductors are made up of elements from different groups in the periodic table, properties vary between semiconductors. Silicon, which is a group 4, is the most commonly used semiconductor material as it forms the basis for integrated circuits, that is IC chips, and is the most mature technology, and most solar cells are also silicon based. A full periodic table as shown in this diagram, in which several of material properties of silicon are given in the page silicon material parameters. A section from the periodic table, more common semiconductor materials are shown in blue. A semiconductor can be either of a single element such as silicon or germanium, a compound such as gallium arsenide, indium phosphorus or cadmium telluride, or an alloy such as silicon, germanium, aluminum, gallium, in which here in this formula X, where this X is the fraction of the particular element and ranges from 0 to 1. So this is all about just an introduction about semiconducting material with the help of this periodic table. Now let's see the band theory of solids. In solid state physics, the electronic band structure or simply band structure of a solid describes the range of energy levels that electrons may have within it, as well as the ranges of energy that they may not have, called band gaps or forbidden bands. Band theory derives these bands and band gaps by examining the allowed quantum mechanical wave functions for an electron in a large periodic lattice of atoms or molecules. Band theory has been successfully used to explain many physical properties of solids, such as electrical resistivity and optical absorption, and forms the foundation of the understanding of all solid-state devices such as transistors, solar cells, etc. The electrons of a single isolated atom occupy atomic orbitals, each of which has a discrete energy level. When two or more atoms join together to form a molecule, their atomic orbitals overlap. The Pauli's exclusion principle states that no two electrons can have the same quantum numbers in a molecule. So if two identical atoms combine to form a diatomic molecule, each atomic orbital splits into two molecular orbitals of different energy, allowing the electrons in the former atomic orbitals to occupy the new orbital structure without any having the same energy. Now let's see the origin of energy bands formation in solids. An isolated atom possesses discrete energies of different electrons. Suppose two isolated atoms are brought to very close proximity, then the electrons in the orbits of two atoms interact with each other, so that in the combined system, the energies of electrons will not be in the same level, but changes, and the energies will be slightly lower and larger than the original value. So, at the place of each energy level, a closely spaced two energy levels exists. If a larger number, that is capital N, of identical atoms come together to form a solid, such as a crystal lattice, the atoms' atomic orbital overlap. Since the Pauli's exclusion principle states that no two electrons in the solid have the same quantum numbers, each atomic orbital splits into capital N discrete molecular orbitals, each with a different energy. Since the number of atoms in a macroscopic piece of solid is a very large number, that capital N is nearly equal to 10 raised to 22, the number of orbitals in very large, and thus they are very close spaced in energy, that is of the order of 10 raised to minus 22 electron volt. The energy of adjacent levels is so close together that they can be considered as a continuum and energy band. If these atoms' electrons interact and give n number of closely spaced energy levels in the place of discrete energy levels, it is known as bands of allowed energies. Between the bands of allowed energies, there are empty energy regions called forbidden band of energies. Crony-Penny model supports the existence of these bands of energies, that is allowed bands and forbidden bands. The mathematical solution of Schrodinger's wave equation is very tedious, but it provides a clue in understanding the origin of energy bands. Figure number 1 shows origin of energy bands formation in solids, showing how electronic band structure comes about by the hypothetical example of a large number of carbon atoms being brought together to form a diamond crystal. The graph on the right hand side shows the energy levels as a function of the spacing between atoms. When the atoms are far apart, shown right side of the graph, each atom has valence atomic orbitals p and s which have the same energy. However, when the atoms come close together, their orbitals begin to overlap. Due to the Pauli's exclusion principle, each atomic orbital splits into n molecular orbitals, each with a different energy, where n is the number of atoms in the crystal. Since capital N is such a large number, adjacent orbitals are extremely close together in energy, so the orbitals can be considered a continuous energy band. In this diagram, small a is the atomic spaces in an actual crystal of diamond. At that spacing, the orbitals form two bands called the valence and conduction bands, with 5.5 electron hole band gap between them. In figure number 2, band structure in individual atom and capital N number of atoms are shown. Atoms have been seen to have discrete energy levels. When a huge number of atoms are combined to form a solid, however, these discrete energy levels are replaced by discrete ranges of energy or energy bands, within which there are so many individual allowed energy values that within the bands the distribution can be considered to be continuous. This idea is shown in this figure number 2. Band formation and how electrons fill them in a metal and an insulator is demonstrated in this animation. In quantum physics, an atom in a box displays discontinuous energy levels. When the number of atoms increased, more level appears until an energy band is formed. In a metal, atoms share some of their electrons. Their energies fill the band from the bottom. These electrons move easily. This allows the metal to conduct electricity well. But when the energy band is completely filled, the electrons become very difficult to move. The material no longer conducts electric current. It is an insulator. The energy level of isolated atom is shown in figure number 3. The energy of electrons is well defined and discrete as shown in figure A. There are number of energy bands in solids, but 3 of them are important to understand the behavior of solids. These energy bands are valence band, conduction band, and forbidden band or forbidden gap as shown in figure B. The formation of the band in the crystal. A crystal, that is the solid, consists of an enormous number of atoms arranged in a periodic structure. If there are n identical atoms, all of them have identical sets of energy levels. In figure C, which shows an atom at the origin of the coordinate system, when the other atoms approach this atom along 3 directions and stay at a distance small a naught, which is a lattice constant of the crystal, as atoms approaches each other, the interaction between them increases continuously. Each energy level splits into many distinct levels and form energy bands. In figure C is sliced at small a naught. It represents the energy band structure of the crystal. Corresponding to each allowed energy level of an isolated atom, there forms an allowed energy band separated by forbidden bands of energy. Here figure number 4 shows energy bands, in which let's see first valence band. The valence band is energy band formed by grouping the range of energy levels of the valence electrons that are engaged in covalent bonding. In the solids, valence electrons are not bound to any particular atom. Therefore, the valence band arises from splitting of the valence energy levels. Second band is conduction band. Conduction band correspond to the energy values of free electrons that have broken their valence bonds and hence become free to move in the solid. It is formed by grouping the range of energy levels of the free electrons. The bottom of the conduction band represents the smallest energy that the electron must possess to become free. Next is forbidden energy gap or band gap. The energy gap between top of the valence band and bottom of the conduction band is known as forbidden gap, and corresponding energy is called as the band gap energy, which is represented by capital E subscript small g. In solids, electrons cannot stay in forbidden gap because there is no allowed energy state in this region. Forbidden gap is the major factor for determining the electrical conductivity of a solid. The classification of materials as insulator, conductors, and semiconductors is mainly depends on forbidden gap. Figure number 5 shows the classification of solids on the basis of band theory. The electrical conductivity of a solid is characterized by the energy gap that separates valence band and conduction band. The ability of electrical conduction is decided by the order of magnitude of the energy gap. In between energy bands, there are ranges of energy which are entirely impossible, known as band gaps. Different substances have different band structures which in many ways state the characteristics of that substance in terms of electrical conduction. As there exists an energy band called the conduction band in which electrons can be propagated as current. The valence band, on the other hand, is the energy level of valence electrons which are bound into the atomic structure of the substance. When a substance is placed in an electric field, its electrons gain potential energy. For a metal, that is the conductor, the conduction and valence bands overlap, and so the additional energy is enough to free electrons and cause current, as there are allowable energy values directly above the initial state. So here energy gap Eg is equal to 0 electron volt. For semiconductors, there is a still band gap, however it is a lot smaller. So energy gap is around 0.7 to 1.1 electron volt. For insulators, however, there is often a band gap between the initial energy state and the next possible value, and so a huge amount of energy is required to cause the electron to be freed and accelerated as current. Therefore, the energy band gap is around 5 to 10 electron volt. This is all seen in the band diagram, figure number 5. Now let's try to understand the properties of solids, that is metals or the conductors, semiconductors and insulators. In metals, that is the conductors, in some solids a large number of free electrons are randomly moving in the entire solid that belongs to conduction band. These free electrons also form a temporary bond with closest ion and are said to belong to valence band. Thus, valence bands and conduction bands overlap and band gap energy is zero. Electrons in the valence band can easily move to the conduction band. Such solids are called conductors. The examples are metals such as copper, aluminum, silver, gold, etc. The concentration of free electrons is about 10 raised to 28 electrons per meter cube. When an electrical field is applied, these large numbers of electrons readily jump into conduction band and current flows in a large quantity. The resistivity of conductors is in between 10 raised to minus 8 to 10 raised to minus 6 ohm meter. The conductivity is typically of the order of 10 raised to 7 mho per meter. In some solids, band gap is narrow and it is of the order of 2 electron volt or less. Valence electrons acquire a small amount of energy from the vibrations of atoms and can move from valence band to the conduction band. Thus, conduction band is partially filled. If a potential is applied across the material, a moderate number of electrons in valence band jumps to conduction band. Hence, current flows in a modest proportion. Such solids are called semiconductors. Example, silicon, germanium, etc. Free electron density is about 10 raised to 14 electrons per meter cube, which is very less as compared to the metals. The resistivity of semiconductors varies from 10 raised to 4 to 10 ohm meter, which depend on several factors such as doping concentration, temperature, etc. The conductivity is typically varies from 10 raised to minus 6 to 10 raised to 4 mho per meter. The classification of solids based on the conductivity or the resistivity and the doping impurity is shown in this diagram. Here the semiconductor classification is shown. Semiconductors are typically classified into two groups. First is intrinsic semiconductor and second one is extrinsic semiconductor. In intrinsic semiconductor, which are called as a pure semiconductors, for example here germanium, silicon, in which number of electrons are equal to the number of holes, that is nothing but Ni, that is the intrinsic charge carriers. Whereas in extrinsic semiconductors, depending upon the impurities like pentavalent impurity, for example phosphorus, arsenic, Sb, etc. The type of this semiconducting material is called as a N-type. In N-type semiconductors, number of electrons are very much greater than the number of holes. Second type of extrinsic semiconductor is P-type, in which trivalent impurities are added such as gallium, boron, indium, aluminum, etc. So these are the acceptor impurities and denoted by capital N subscript capital A. In P-type of semiconductors, number of electrons are very much less as compared to the number of holes. So in N-type semiconductors, maximum number of charge carriers are electrons which are negatively charged. That's why it is called N stands for negative, so N-type. Whereas in P-type semiconductors, maximum charge carriers are holes which are positively charged. That's why P stands for positive. So these are the two important types of extrinsic semiconductors, that is N-type and P-type. Following diagram shows the intrinsic semiconductor. The germanium and silicon are the most common type of intrinsic semiconductor elements. They have 4 valence electrons, that is tetravalent, They are bound to be the atom by covalent bond at absolute zero temperature. When the temperature rises due to collisions, few electrons are unbounded and become free to move through the lattice, thus creating an absence in its original position, let's say hole. These free electrons and holes contribute to the conduction of electricity in the semiconductor. The negative and positive charge carriers are equal in number. The thermal energy is capable of ionizing a few atoms in the lattice and hence their conductivity is less. The lattice of pure silicon semiconductor at different temperatures, in which at absolute 0 Kelvin temperature, at this temperature the covalent bonds are very strong and there are no free electrons and the semiconductor behaves as a perfect insulator. Above absolute temperature, with the increase in temperature, few valence electrons jumps into the conduction band and hence it behaves like a poor conductor. The conduction mechanism in case of intrinsic semiconductors is shown in this diagram. Now let's see the extrinsic semiconductor. The conductivity of superconductors can be greatly improved by introducing a small number of suitable replacement atoms called impurities. The process of adding impurity atoms to the pure semiconductor is called doping. Usually, only one atom in 10 raised to 7 is replaced by a dopant atom in the doped semiconductor. An intrinsic semiconductor can be further classified into N-type semiconductor and P-type semiconductor. All these details we have already discussed in previous block diagram. Therefore, for the N-type semiconductor, let's see in detail majority electrons and minority holes. When a pure semiconductor, let's say silicon or germanium, is doped by pentavalent impurity like phosphorus, arsenic, bismuth, etc., then 4 electrons out of 5 valence electrons bonds with the 4 electrons of germanium or silicon. The 5th electron of the dopant is set free. Thus, the impurity atom donates a free electron for conduction in the lattice and is called donor. Since the number of free electron increases by the addition of an impurity, the negative charge carriers increase. Hence, it is called N-type semiconductor. Crystal as a whole is a neutral, but the donor atom becomes an immobile positive ion. As conduction is due to the large number of free electrons, the electrons in the N-type semiconductor are the majority carriers and holes are the minority carriers. Now let's see the P-type semiconductor. Majority holes and minority electrons. When a pure semiconductor is doped with trivalent impurity, let's say boron, aluminium, indium, gallium, etc., then the 3 valence electrons of the impurity bonds with 3 of the 4 valence electrons of the semiconductor. This leaves an absence of electron, that is the hole, in the impurity. These impurity atoms, which are ready to accept bonded electrons, are called acceptors. With the increase in the number of impurities, holes, the positive charge carriers are increased. Hence, it is called P-type semiconductor. Crystal as a whole in neutral, but the acceptor become an immobile negative ion. As conduction is due to large number of holes, the holes in the P-type semiconductor are majority carriers and electrons are minority carriers. Now let's see insulators. In some solids, band gap energy is very wide, which is greater than 5 electron volt. The electrons are tightly bonded to atoms and it would require very large amount of energy to raise an electron from valence band to the conduction band. Very few electrons can get this large amount of energy at ambient temperature, hence there are only a few electrons present in the conduction band. When potential energy or the potential difference is applied across them, a negligible current flows and solid exhibits very low electrical conductivity. Such solids are called insulators. For example, glass, wood, mica, etc. the free electron density is negligible. The resistivity of insulators vary from 10 raised to 12 to 10 raised to 16 ohm meter, and the conductivity is typically 10 raised to minus 12 mho per meter. This is all about the band theory of the solids and the classification of the solids based on the electrical conductivity and the resistivity. Also, we have seen the classification of the semiconducting material, that is intrinsic semiconducting materials and extrinsic semiconducting materials. In my next lecture video, I will discuss about effective mass of electron and density of states. So please don't miss my next lecture video. Thank you. Below this video, in the description, the link of important information related to this video is given. Please go through it. Please like and share this video and subscribe to Dr. Khalkar's Classroom channel to get the notifications about my upcoming videos. Thank you.